In this session, we are going to look at one of the applications of Archimedes principle. We are going to describe some procedures on how to measure relative density of a liquid using a balanced lever. And this is how our procedure is going to be like. Of course, right there, what we have there is a balanced lever. That's a lever with a weight whose W, this is a known weight, we know this weight, W. Of course, D1 is going to be the distance from the known weight to the pivot, then D is going to be a fixed distance that we are going to maintain throughout our experiment from our pivot to a weight whose W1, which weight we do not know. So to begin off, of course, we are going to use a known weight and we are going to balance this known weight with this sinker that we have, whose weight is W1. We are going to balance them, and after balancing them, we shall get the distance D1 from the pivot to the known weight and the distance D. After balancing them off, we measure and record D1 and D. And when we do so, we shall take moments about this pivot. Now, I assume by the time you're watching this video that you are well conversant, or you know what I mean by principle of moments. Of course, principle of moments is that clockwise moments are equal to anti-clockwise moments. So we are going to take moments about that pivot, and so it's going to be that W1 times the distance there is it going to be equal to W, multiply that by the distance D1. Now we're interested in finding the weight of this W1. So it means that we make W1 the subject of the formula. When we make that the subject of the formula, this is going to end up being W times D1 over D. We call that our expression 1. Our expression 1 is actually the weight of this sinker. And let's call this, the weight of the sinker is more like saying the weight of this sinker when it is in air. After that, we are going to immerse this sinker in water. So this sinker is now immersed in water, as we have seen right here. The sinker, after immersing it in water, we definitely, remember, we keep this D constant. And so what we do is that we are going to adjust the distance between the pivot and the known weight until this lever balances. And when it balances, we measure and record the distance D2 and definitely after measuring the distance D2, we go ahead and take moments about the pivot. Taking moments about the pivot in this case is going to give us the weight W2, multiply that by the distance, the constant distance D is equal to the known weight W times the distance D2. So meaning our W2, our new weight when this sinker is in water is given by W, multiply that by D2, divide that by D. So that is our second expression, W2. So we are going to repeat this same thing, but instead we are going to dip this sinker into a liquid whose relative density we are looking for. And that is exactly what we've done here. We have kept this D still, it is still constant. We take away the water and so we dip this sinker into a liquid whose relative density we are looking for, and we adjust this weight, this known weight, and we get another distance from the pivot. We call it D3. And after doing that, we go ahead and find moments about the pivot. Clockwise moments, we take moments about that pivot, so it means that it's going to be W3 times the distance D. W3 times the distance D is going to be equal to the known weight W, multiply that by the distance D3. So W3 in this case is going to become W, multiply that by D3, divide that by D. And this is the third expression right there. Now if you already realize, you see that actually we are using this lever to try to get us the weight of this sinker in three different conditions. We first got the weight of that sinker when it was in air. Then again we got the weight of that sinker when it was in water. And again, we got the weight of that sinker when it was in a liquid, whose relative density we are looking for. So from our theory, we know that relative density of a liquid is, we are going to get the apparent loss of weight of the sinker in the liquid, divide that by the apparent loss of weight of that sinker in water. And so if I may use abbreviations here, the apparent loss of weight of the sinker, or of a solid over a substance in the liquid, in this case it's going to be the weight of the sinker, or the weight of the substance in air, minus the weight of the sinker when it is in the liquid, divide that by the weight of the sinker when it is in air, minus the weight of the sinker when it is in water. This difference in weight is the same as saying the upthrust experienced by the sinker when it was in the liquid, divide that by the upthrust that was experienced by the sinker when it was in water. The weight of the sinker when it is in air is W1. It is what we got here when we put it on lever, when W1 was hanging just alone. This is the weight of this sinker when it is in air. So it means this is the same as saying this is going to be W1 minus the weight of the sinker when it was in the liquid, according to our experiment, when the thing was in the liquid whose relative density we want, that was W3. So that's going to be minus W3, divide that by weight in air, which is W1, minus the weight when it is in water. And from our experiment, the weight when it was in water is W2. So we will go ahead and make the necessary substitutions. What is W1? W1 is W times D. This is given by W times D1 minus, divide that by D, minus W3. W3 is given by W times D3, divide that by D. Divide all that by W1 still, which is W times D1 over D, minus W2. What is W2? W2 is W dot D2. W multiply that by D2 over D. And of course, this is going to become W dot D1 minus W dot D3. Divide that by the LCM here becomes D. Divide that by this, which is going to become W dot D1 minus W dot D2. Divide that by the LCM here is D. So this is going to end up being, W is common here, so we shall put W outside the brackets into D1 minus D3. Divide that by D, divide that by W is common, so we put W outside the brackets here into D1 minus D2, divide that by D. So this becomes W into D1 minus D3, divide that by D, multiply that by, with right here the reciprocal over W into D1 minus D2. And this is definitely going to end up with, this W cancels with that one, this D cancels with that. We end up with an expression as D1 minus D3, divide that by D1 minus D2. And with this expression, we are able to measure the relative density of a liquid using a balanced lever. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.